everybody. We're going to do a little bit of quick review of this most general possible way to couch expectation maximization. So far, we've been showing you the idea of EM in very specific applications, like k-means, where all we're doing is updating the means, and in the generalized mixture model, where we're updating all the parameters of the distribution. But this is, fundamentally the same process can more generally be used to estimate either maximum likelihood estimates or a full variational Bayes kind of situation where we're estimating parameters and distributions of parameters. Okay, so I want to walk you through this because this kind of notation gets a little confusing because it actually looks different than what we've seen so far. So that's what we're after right now. Let's go for it. So again, I want to remind you that the idea here is that it might be hard to calculate the probability of X, the probability of our data. And it can get easier if we induce this idea that there is not just our data, but actually a set of hidden variables called latent variables that we're going to notate by Z. Okay? And by breaking up what was just probability of X into the probability of X and Z into the joint probability, and then summing over all the possible values of Z, right? We can get to this actually dropping out to be better math for us. So again, this is our goal. We want to estimate the probability of the data given the parameters of the model. But we're going to assume that the data is also influenced by these latent variables. A reminder, what have we seen so far in a mixture model or in a k-means? These hidden parameters Z, that's, hey, what cluster does this data point belong to? What actual cluster generated this data point? And that assignment was our Z's. Okay? But it's more general than that. We can use any set of latent variables and do this. Okay. So, here's the dealio. What we want to do is we want to maximize this thing that we care about, right? Well, the way we're going to do that, as always, is we're going to take the log of that probability function, right? We're going to take the log of the probability function. This log likelihood, the reason we do it is that logs are, of course, quadratic, and we can optimize. We can set the derivative, find the derivative of this log likelihood function, set the derivative equal to 0, solve for the parameters that do this best. Okay. Well, the funny thing is because this log likelihood is a summation over the Z variables, well, we can break this up into two parts. First, we have the log likelihood, that's what that cursive L means. It means the log likelihood of this thing we haven't yet observed, this distribution Q. And this distribution Q is a distribution over the actual latent variables, the things we can't measure directly. Okay? And this P is the thing we've already been looking at, right? It's our probability of X. Okay? So the probability of X given the parameters, that is this P in here. Okay, so what we're saying here is that the likelihood function of X given the parameters, we can break it up into two chunks. The likelihood of the Z and the difference between this Q distribution, the Z-based distribution, and the X-based view of this thing. Remember, what is the KL? The KL is the Kullback-Leibler divergence, and it is a measurement of the difference between two distributions. In this case, a distribution based only on X's, and a distribution based on X's and Z's. Okay? And that's what you're seeing here. This is the definition of KL, couched in terms of Z's and X's. And this is just the likelihood distribution on the Z variable. Okay. So the graphical interpretation of this is really nice, right? Whatever the likelihood is of the data given the parameters, that's this big chunk. We're just breaking it up into two sums, the likelihood of this Z parameterized version of it, and the difference between the Z parameterized and the X parameterized. Okay, so again, this whole Q thing gets super, super confusing to people. I'm not a big fan of this version of the notation. Why do we keep saying Q? Because really, what we're talking about is this, right? P is just like, it's the probability of the latent variables given both the data and the parameters. Now let's think about this for 1 second in terms of what we've already been playing with in latent variables, where the Z is just, hey, which cluster generated this data point? So this is the probability that cluster 1 generated this data point given the data and those parameters of those clusters. Okay? So Q, when you keep seeing this Q, it just really confuses people in general. But I just want you to keep in mind what Q is. Q is simply the probability of these latent variables given data and parameters. Okay, and the KL divergence is the difference between that Q likelihood function and that is the Z-based likelihood function and the X-based likelihood function. Okay, so that is really what you need to know. Okay, we can see that they're going to repeatedly give us the likelihood function in terms of summing over all the possible Z, all the possible latent variables, right? The probability of Z given the data and the parameters. And then we're going to end up, this is a likelihood function, so it's the probability times the log of the probability, yeah? And the thing is that, once again, we have the inverse here, right? We're looking at the situation where we're doing a two-step, and what we're looking at is this likelihood function is that we are doing an update, right? We are starting from some estimate, and we're doing an EM two-step, right? We have the old parameters, the theta old, and those thetas describe what we assume are the centers and the variability, the variances of each one of these clusters. And then we have to estimate the likelihood of membership at a given data point belongs to a given cluster. And then once we've assigned data points to clusters, then we're going to use the empirical means and the empirical covariance matrices to update our estimates of those parameters. So we're doing this two-step. We're starting with the old assignments, we're going to calculate likelihoods, and then we're going to update assignments, and then we're going to use those updated assignments to, once again, calculate new likelihoods. Okay? Now, the thing is because of that KL divergence, because they're, the parameterizing this in terms of latents is only going to be such that we have this situation that we started with, right? Where, this latent parameterization is just not going to, it's either going to be the same size as parameterizing it in terms of the data, like when this KL divergence is 0, then the Z parameterized version of this idea is the same as the X parameterized version of this idea. Okay? When the latent variables don't do anything, then the KL divergence is going to be 0, and these two are going to be the same. But in general, we always know this blue line is a lower bound on the X-based probability distribution. Okay? So what we know is when we do an update, when we move from some old Q to some new Q likelihood, then we know that the P likelihood has moved at least that far up as well. Okay, so this is the picture that they're trying to give us, right? We go to an update, we move from this old value of the Z-based likelihood into this new value. And that means that the X-based likelihood has gone up at least that much. Okay, so maybe this is like the better picture, right? So reminder, there is in general some likelihood function which, parameterizing it without those latent variables is in general maybe a pain in the butt. Maybe that likelihood function over the probability space of models here, right, is not quadratic. That can happen in general. By breaking it up with these latent parameters, we are guaranteeing that it's a quadratic. This blue line is the current estimates, the current assignments of data points to clusters, the current Z value. The current Z value and the current estimates of the model parameters. Okay? So we use this likelihood function, we update our model parameters, go from old to new. That movement from old to new shifts us from this blue line to this green line. Right? We have a new parameter, a new Q, a new log likelihood parameterized by this latent variable Z. And that likelihood, well, it's moved up, right? And everywhere that we don't quite match the red line, well, that gap, that's the KL divergence. Okay, so in general, again, what we're doing is if we assume that every single data point is drawn independently from the distribution of X's and Z's, right? So in those cases, we can just write this thing as a product over all the different data points. Okay, again, this is that Q value, right? The probability of Z given X and the data X and the parameters of the model theta. Okay? So this is just going to be a product of all the individual data points, okay? Summed over, divided by the normalization term, which is the same thing, but summed over every single latent variable Z. Okay? So, this brings us to the final formulation, right? Where we can take this thing that we want to calculate, we can break it down into a latent variable bit, the difference between the latent variable and formulation and the X-based formulation, right? And then these are the constant terms that have the prior distributions on data and the parameter space. Okay? And again, when this KL divergence bit disappears, well, when it goes to 0, that's when our latent variables don't give us any information. Okay, and in general, we know that when we deal with this Q, with this parameterized version, which we know is quadratic because we've picked that form to make it quadratic, we're optimizing this potentially non-convex X-based form because we have this picture, right? Where we know that this quadratic, this convex Q form of the likelihood function is a lower bound on the potentially non-convex X-based form. Okay, I hope that's helpful. I think that's as far as I wanted to go. Yeah, okay. Good luck, everybody. We're gonna get into some, more intuitive formulations of this and show you how we can use this stuff to do things like estimate missing values from data. Okay, talk to you in class. Bye.